When we talk about empirical formula, the theme for empirical formulas is right here. We're looking for the smallest whole number ratio. And what that's dealing with is the smallest whole number ratio of atoms within a compound. Okay? We'll also talk about molecular formulas a little bit later on today, but molecular formulas are what they are. All right? They're not the smallest whole number ratio. Sometimes, and this will make you upset, sometimes the empirical formula is the molecular formula. Okay.
Why would they do that?
I know. That's the way God made it. So. But what we want to do is make sure that we have the smallest whole number ratio within the compound. Okay. So, and what we're going to do is, we talked about percent by mass, percent composition by mass the last time, and we can use that to help us to determine the empirical formula. But when we look at masses on your periodic table, and I know you have your periodic tables out already, but when we look at the masses on the periodic table, if you look at the mass for, say, hydrogen and compare it to carbon, those masses are identical, aren't they? No. However, on the periodic table, those masses represent what? The moles. So if I had 1 mole of hydrogen, then the mass is 1.008. If I had the mass for carbon, then it's 12.01. So I can take those masses and get something that we now have that's equal, and that's the number of moles. So we always, whenever doing empirical formulas, we always want to change our mass to moles before we even try to do any ratios. Don't ever look at masses and just say, I got 50 grams of this, 50 grams of that, that's a 1-to-1 ratio. Unless it's the same thing. Okay, so always convert to moles. And I don't know how many other, and we'll do some examples on the board.
No.
Oh, no.
All right, we'll work that practice problem out.
Yeah.
Or those practice problems out.
No. I don't know.
All right. And there's part of the homework problems.
All right, we're done, right?
No. There's a blank here for the empirical formula here. Nothing really additional to what I just said. Okay, I don't know why I actually broke it off into sections, but don't worry about it. Just get that blank. And we should have some more. And empirical formulas are pretty fun. Yeah, they are. Yeah, they are. They're not as fun as stoichiometries, but they are fun. There's another blank there. Whole number ratios. All right, we'll do these as well. Man, that's 4 practice problems. Hey, there's some more homework. Molecular formulas. Okay. When doing molecular formulas, typically, unless I'm a nice guy, you need to determine the empirical formula. Sometimes I will give you the empirical formula so then we can just go and solve for the molecular. Now, that doesn't mean anything to you yet because we haven't worked any problems out. But molecular formulas are not the smallest whole number ratio. They are what they are. Now, this equation right here is what we're going to use as our multiplier for our empirical formulas to get the molecular. Okay? So this is pretty important. Number. And we'll work it out here in a second. And I think we're ready to turn the lights on. Yep. Oh, look at all of it. We got 6 practice problems today. This is awesome.
Don't turn the lights on. I don't have clothes on.
What?
I don't have clothes on.
We're doing 3s, 4s, and 5s.
All right, let's look at page 15, I believe it is, the first practice problem. And you will need your calculator. You will need your period number. Let's look at page 15. Page 15, number 1, it says, determine the empirical formula for a 400-gram sample containing 31.5% cobalt, 34.28% sulfur, and 34.22% oxygen. Now, there's a smart way to work this out, and then there's a long, tedious way to work this out. Okay? So I'm going to show you the smart way. I'm not going to show you the other way. Now, even though I gave you a 400-gram sample, we're going to ignore that. And we're going to go right to the percents. Okay? Because if I say that I have a 100-gram sample or a 400-gram sample, do the percents that I've given you change? No. So it doesn't stand to reason that we want to find out how many grams if the percents will be the same regardless of the sample size. So whenever you are given a percent, just treat it like it's a 100 gram sample, okay? Even though I'm giving you information that's telling you it's not a 400 gram
So
sample.
it's useless information.
Bingo. Okay, it's a distractor. It's actually trying to tease you to do more work when it's not necessary, okay? However, we do have this information. We have 31.5% cobalt. So we have cobalt, and it's, was it 31.5%? But I'm not going to change, or I'm not going to write percent, I'm actually going to write grams. I'm going to pretend I have a 100 gram sample. What we want to do is always change the mass to moles. Okay. And then we have sulfur, which is 34.28%. So again, change that to grams. I do know that's 32.06. And then oxygen, we have 34.22.
Cobalt is 58.93.
58.93. Thank you. And that's 1 mole of cobalt. And what was the bottom of the oxygen? And that's 16. Okay. Now, don't fall for the trap, because a lot of my AP kids do this. They'll see this as oxygen and automatically write it as O2. Whenever we're doing empirical formulas, we're looking at what's on the periodic table. So we don't have diatomics in empirical, all right? So then we're going to get some values here. And what will my units be for each of these values?
Moles.
Moles. That's really important. Okay. And if I had 1 mole of cobalt and 1 mole of sulfur, that means I had the same number of particles. It would be a 1-to-1 ratio, but I doubt if I do. So we've got 0.5. Let's go at least 4 decimal places. We don't want to round too much here. Rounding too much can be dangerous. So 1.0692. Okay. And then the last round, 2.1388, we'll say. Okay. So now, here's our mole amounts. So this tells us how many particles we actually have within this compound of cobalt, sulfur, and oxygen. Okay. What we want to do if we want to find the smallest whole number ratio is we have our mole amounts, which quote unquote are the equalizers here. We want to find the smallest value here, and then we're going to divide everybody by the smallest value. So it looks like the cobalt's the smallest, so we're going to divide everybody by that value. So that's 1. Don't even have to do that one in your head. Let's make that a 3. 3, 4, 5. It's probably 2. I'll come back to that here in a second. So this is a 4 down here, and this is a 2 here. Everybody good on that?
Are those whole numbers really?
They're very, very close. In other words, like this one down here was 4.001. Okay. And then this one was something. What is it?
1.968.
1.968? Ooh. I got 2.00037. Okay. So it's really, really close. Now, we want values that are very close, and we'll talk about fractions and decimals here in a second. But if it's like 0.00 or 1.99 something, go ahead and round it to that. Okay. So here's our ratio. We have cobalt 1, sulfur 2, oxygen 4. Now, do we ever show 1 as a subscript? No. Okay. So there it is. 1 cobalt, 2 sulfurs, 4 oxygen. S2O4 is not one of your polys. Okay. It's just that easy. Okay, that's the empirical formula. Looking at the smallest whole number ratio. Think you could do that?
No. What's the long way?
No, I'm not doing the long way. The long way is actually take those percents and multiply it times 400 grams, get a gram amount, and then do the number of moles. Now, you will not get the same number of moles, but you will get the same ratio. So you don't want to do an extra step. Now, this is a short way. He asked about the long way. The long way would involve one more step, and I'm not going to show that because I don't want anybody to even do that.
Everybody thinks.
All right, let's look at the second one. Number 2. It asks, what is the empirical formula for a 425 gram sample containing 69.94% of iron and 30.05% 30.06 gram or percent of oxygen. So again, that 425 is a distractor. Don't do it. So we have our iron, and we have 69.94%. So just pretend you have a 100 gram sample. That's the easiest way to do it. And then what is the other one? Oxygen, and that's a 30.06 grams. And iron is, okay, so that's like 1.25, we'll say 2.3, and then 0.8788. What's that? What's the matter? Okay, which one's smaller?
Iron.
The iron, so divide everybody by the smallest number of moles. 5, 2, 3. And we get 1.5.
But you round that to 2.
Do not round that.
Oh.
Okay. The reason why if we round that, that's too big of a number to round. So whenever we have a decimal, we should be looking for something when we have a decimal value, or when we get to the end here, okay? You'll either end with a 0, 0.25, 0.3 repeating, or we'll say 3.3, let's say that, okay? Half, 0.66, 0.75, and 1. These are the acceptable decimals that I will give you, okay? I will not give you, if you get a value, let's say that it's like 0.29 as your mole ratio, not over here, we don't care about these values over here, we care about these values here. So if you get a decimal where it's 0.29, you messed up. I'm just gonna be honest with you, you messed up. So if we have these decimals, this is where we're shooting for. And what we wanna do is, we wanna change these to fractions. Okay, so that's half, it's 2/3, and that's 3/4, okay?
Could that also have a 1 in front of it?
They could have any value in front of it,
Right.
yeah. So what we wanna do is, we're gonna change that 0.5 to a fraction, which is
1 and
1
1/2.
1/2, okay?
Can we change it to an improper fraction?
Don't. Yeah, don't do that. Now, what we're going to do is, again, in our chemical formulas, you never have partial subscripts. They have to be whole. So what we're going to do is, I'm going to multiply both of these by what value to get a whole number? 2. Very good. So whatever value is in the, what is that, denominator? Okay. We're going to multiply everybody by that value. Okay. Now again, this is our acceptable range. So we're going to either go for 0, for 1, or a whole number here, and if not, this is our decimals that we'll work with. So this gives us a 3, and this gives us a 2. Yeah, probably wouldn't be a bad idea to have that.
Wait, how'd you get 3?
1.5 times 2.
Oh, okay. So
Yeah.
you take the whole thing.
Yeah, so we're going to multiply everybody by 2 on that.
Get rid of the denominator.
Yeah. So if I multiply that, that gives me 1, then that's 2, so add those up, that's 3.
Craig, you worded the homework problems weird.
Did I? Okay, well hang on, let me finish this one first. So this is our chemical formula. Does anybody know the name of this one? This is something we should be able to name.
Iron trioxide.
Not tri. I'll give you the iron part. Iron's a metal, right?
Yeah.
So it has a charge of either what or what? Look on your periodic table. What's the possible
Iron
charges?
2.
2 or 3. What's the charge on oxygen?
2.
-2. How many do you have? 3. How many irons do you have?
Iron 3.
Iron 3. So sometimes I may even ask you, what is the name of the compound? If it's something that you should know. Okay. The last example where we had cobalt with 2 sulfurs and 4 oxygens, that's not one of your 10 polys. But this is definitely something we should be able to name. Okay. All right, go ahead and ask me about the homework.
Okay.
Which number, first of all?
It just says right under homework problems. That question right there.
What are the empirical formulas for the 2 sulfur oxide compounds? Is that what you're asking?
Yes.
So if you have two sulfur oxide compounds, what are the compounds made up of?
Sulfur and oxygen.
Yeah, so they're made up of sulfur and oxygen. And in 3A, I gave you the percent of sulfur by mass, but I didn't tell you what the oxygen is. But I think,
Isn't it 50?
whatever. If you have two things and one of them's 50%, then
The other one has to be 50.
there you go. Okay.
Gotta be 35.
So that's where that's going. Let's take a look at the next practice problem.
So that
On-
means sulfur is 40%.
Don't give it away.
18.
Page 18. All right, the next practice problem. It says when iron 3 oxide, and the formula is given there, reacts with 18.94 grams of aluminum metal, iron is produced along with 35.74 grams of aluminum oxide. What is the empirical formula for the aluminum oxide? Okay, so it says that we have, let's write this down. So we have 18.94 grams of, what is that, aluminum metal? So Al. And it says, and it doesn't do anything with the iron oxide, which is kind of fun. It says iron is produced along with 35.74 grams of aluminum oxide. So we don't know what these are. Okay, and it wants to know what is the empirical formula for this aluminum oxide. Okay, so we have the mass of the aluminum, which is 18.94 grams. So we definitely can convert that to moles. Was that 26 point?
Wait, are we
98.
doing another one of these? 'Cause I'm already-
Okay. And
I have a question.
yes.
How don't we know the subscripts on those? Can't we just use our charge?
That's a check later on.
But what-
So if we know the aluminum's mass, how are we going to be able to determine this if I didn't give you the oxygen?
Wait, I'm
100 minus.
No.
I don't know.
What have I given you? The mass of the aluminum oxygen compound and the mass of the aluminum. So how can we find the oxygen?
Subtract them.
Take the difference, yeah. So the difference of the two will give us our oxygen. So whatever the difference of 35, oops, turn the power on. So I'm trying to get you guys to do a little problem solving, which
Yeah.
I know you guys like.
My best attribute.
There you go. So our oxygen is 16.8 grams of oxygen. So now we have that. Then we can do some solving here.
I don't get, what are we gonna find?
What's the last part says, what is the empirical formula for aluminum oxide?
So you're trying to find the little number.
Yeah, we're trying to find these values here. And actually, if I went with X and Y, that might be a little friendlier to you.
There you go.
Okay, my bad. So this one gives me 1.05, and that's moles. Like 0.7020. Okay. Which one's smaller?
7020.
Good. So we'll divide that by both of those. There's a 1. And let's see. 1.05. And what does this give me?
You're going really quick.
And again, I erased my things over here.
1.5.
1.5?
Yeah.
So instead of writing 1.5, what should I put there? 1.5. Good. Now you can write 1.5, but then erase that 0.5 and put 1/2. So what are we going to multiply these both by? 2. We won't always multiply them by 2, but whatever's down here, we definitely want to multiply it by. Both, and you have to do both of them. Now, Keaton was saying that can't we just figure out? Of course, that's a good check. So we have how many aluminums? 2. We have how many oxygen? 3. And oxygen's -2. We have 3 of those. Aluminum, we have 2 of those. And what's the charge on each aluminum? +3. So that's a quick check. Okay.
Why do we do all that work for that?
To make you feel good about yourself, that you can do something. 2. It says, propane is a gas commonly used for cooking and heating.
Who cares?
Good.
Isn't that awesome?
Who cares?
So if you didn't know,
So 42.
all right.
Let's just
It contains the elements carbon and hydrogen. That's important. Okay. When 72.06 grams of carbon, let me write that down. 72.06 grams of carbon reacts with hydrogen gas, 88.06 grams. Propane is produced, and again, propane is made up of a carbon-hydrogen compound. He wants to know what's the empirical formula. Okay. So again, what do we not have that we need?
The grams of hydrogen.
Good, the grams of hydrogen. So we need to find the hydrogen. So take the difference of those. What is that? 16? Is that right?
Yep.
Okay. Okay, so we can like ignore that value there. So, what?
You just said, what don't we know? Carbon.
We don't know the hydrogen. Did I say carbon?
I think you
Strike that from the record, make that hydrogen. Okay, so we know the carbon.
You're talking to technology now, Craig.
I know.
What are you doing with your life?
A lot of things.
The good thing about technology, it doesn't argue back. Yet. Yet.
Say? I don't know. You see a transformation before? It hasn't turned yet.
So find out how many moles of each. So I believe that's 6, and we'll say it's 6.0. It came out pretty nice there. And then 16 divided by 1.008. So that's 15.87.
Siri's just some lady making you feel good about yourself.
Why is that mean?
7.3. Okay. Actually, let's be smart about this. Let's make that 1.0, because I don't think I designed that question very well. So if I did 16 divided by 1, what is this value here?
16.
Let's make that. Just to make life easy on yourself. I know, my bad. All right, so we have 6 and 16. Which one's smaller?
Same as I think.
So that gives me a 1, and that gives me a, not something but 6 repeating. Uh-oh. So if it's 2.6 repeating, 2 2/3, good. So let's write it as,
Multiply by 4?
we're going to multiply by 3.
6, 3, I don't know.
Well, what's the bottom value?
Oh, 2.
3, right? So we'll multiply by 3 on both of these. So the top one is 3. What's the bottom one?
8.
8. Very good. And so there's our values. So C3H8. And if you know propane, that's the formula.
So if I knew propane, I could just write that down.
After you show all your work. On page 21, the first practice problem, it says, the empirical formula for a common drying agent is P2O5. Well, that's nice of me. P2O5. And this is the what again? The empirical formula. So this is our empirical formula. So do you have to do all the work that we just did in the other examples? No, it's already done for you.
But are there going to be ones where you make us do that too?
The next
Oh,
one.
there'll be, yeah, I'll make you find the empirical formula and then find the molecular.
Put all of that useless information.
Well, hang on, we're still on number 1. We're still on number 1. It says the molecule has a molar mass of 283.88 grams per mole. It wants you to find the molecular formula of the compound. Now in the notes, I showed you quickly that to find the molecular formula, you first need the empirical formula. And then what you'll do is you'll take the empirical formula, you'll take the empirical formula, listen, and there's a multiplier for the empirical formula, because again, the empirical formula is a small to number ratio.
Putting it in right there.
So I gave you the molecular formula mass, which I must do every time. So what we're going to do for N is, you're going to take the molecular formula mass and divide it by the empirical formula mass. That will give you the multiplier. Okay? So the molecular formula mass in this problem was given as 283.88 grams per mole. Now if you want to include the units, that's fine. They're going to go away. So how in the world do you think we're going to find the empirical formula mass for this?
Use little subscript things.
Yeah.
And take the molecular mass off.
So the empirical formula mass is based on finding molecular masses. So we have 2 phosphorus, which is 30.97.
That's gonna go at the bottom.
It will go down here, but I'm going to find the empirical formula mass first. I don't want to put all that work down here, but you can if you want.
Is that 997?
That's 30.97, and then I'm going to multiply that or add that to 5 times 16.
Well,
What did I get?
give us a big number.
141.94. Okay, and that is the empirical formula mass, molar mass. I'm going to take that divided by that,
But then you don't have a
and what value do I get there?
2.
2. N will always be a whole number. Okay, and it should be really, really close to a whole number. Okay, it shouldn't be like 2.5 or 2 1/3 or anything like that. It should be a whole number. So what we'll do is we'll take our empirical formula, and since we have a 2 there for our N, what will that molecular formula be? P4O10. Okay. Empirical small cell number ratio, molecular. Last practice problem. Oh, so sad that it's the last. Look at all that. That's awesome.
I bet half of those.
Hydrazine is a widely used compound. It can be used to treat wastewater from chemical plants, removing ions that may be hazardous to the environment. So this is beneficial to the environment. It can be used as rocket fuels. It can help prevent corrosion in pipes of electrical plants. Oh, here we go. In a 32-gram sample of hydrazine, there are 28 grams of nitrogen. Oh, here we go. 28 grams of nitrogen. Got it. Check. And 4 grams of hydrogen. Does that equal 32 grams?
It sure does.
Okay, so we don't need to do anything to 32 grams, right?
No.
And then it said the molar mass of the molecule is 32 grams. Whoa, that's crazy.
Why would you do that?
All right. What is the empirical formula of the hydrazine? So, find your empirical formula first. So 1 mole of nitrogen.
Wait, what are you doing this for? Oh.
Find the molecular formula. I know, right? And let's get some numbers here. So 1.9987. We'll say that's 2. Okay? Or do you? Oh, here, I'll make you guys happy. Let's do that. I don't want any unhappy customers out there. 998.6. How's that? Okay. And then 3.9683. Okay. Yeah. All right. So which one's smaller? Top one, good. So 1.9986. That'll give me a 1. 1.9986 should give me a what? 2. Okay. So what is the empirical formula for hydrazine? NH2. Good.
Oh.
So,
to find the molecular formula, what do we need to do to that?
get the numbers and add them.
Get the numbers. I like that.
Add them together and put them on the bottom.
Okay. So 2 times that. So around 16-ish and some change. Okay. There's that 16.026. So if we put that up there, we get like 1.999 something. 996, which is 2. Good. So the empirical formula for I'm writing ammonium there. That's bad. So that equals N2H4. Isn't that awesome?
Beautiful.
You're almost a true chemist now.
Is it said Kids grow up.
I know. Yeah. All right, so 3s, 4s, and 5s.